In this video, we are going to discuss 6 basic elements of a communication system. This is according to Chapter 3 of the book Software Receiver Design. These 6 elements are oscillators, linear filters, samplers, static nonlinearities, mixers, and adapters. Here is a PAM communication system, pulse amplitude modulation communication system building block. We see from the top line, that's the transmitter. We have a binary message sequence B encoded into samples -3, -1, 1, 3, going through a pulse shaping filter and then become a analog waveform upconverted to the radio frequency, then transmitted through the channel. The channel may be shared by some other users, so we can use the frequency division multiplexing to adding the signals from other users and adding the background noise of the channel, and then arrive at the receiver. The middle line is the receiver from the antenna. We have analog conversion down to the intermediate frequency, and then sampled to the discrete time signals. Digital down conversion to baseband. Compensate with carrier offset, carrier synchronization. Then we have a post-matched filter. Doing the matched filtering, get the best possible samples. Then downsampling if needed, working with the time synchronization to correct with symbol offset and frame offset. Going through an equalizer to retrieve the signal of the interested band, then make a decision. They can be the hard detection of each of those sample points of -3, -1, 1, 3, decoding into bit stream and reconstruct the information message. We will select 6 elements for individual discussion as the basis for system design. And the first one is oscillator. So the oscillator is to create a sine wave. It can be used as part of the analog up conversion and the down conversion. It's here, so this is an oscillator. The second part is linear filter. Linear filter is used as the equalizer. For example, in this block diagram, that's the linear filter. And the system nonlinearity will be implemented in many different aspects of communication system. In this case, the nonlinearity can be used for the analog up conversion. So this is the nonlinearity. When we are trying to change a signal from one frequency to the other frequency, we have to pass the signal through a nonlinear filter. A linear filter will not change any frequency components. And the fourth is sampler. Sampler is when we are doing this analog to digital conversion. So here I have a sampler here. The mixer is when we are doing the frequency division multiplexing, adding the information from other users. We're going to use a mixer here. And lastly, the adapter. Adapter is used at the receiver, for example, the carrier synchronization and the timing synchronization. We're trying to trying to combat any of those small changes due to the frequency offset, due to timing issues. And these are the basic elements that can be used in the big picture of this building block. Here shows different functionalities of these 6 elements. Each element works on the signal. We can see that effect in the time domain and also in the frequency domain. For example, using the linear filter, here we have an arbitrary signal in time domain. And if we are doing the Fourier transform, look from the frequency domain, the signal looks like that. The y-axis is the magnitude. Now I want to filter out the high frequency component of the signal, so I apply a low-pass filter. Therefore, the low-pass filter may look like this, multiplied by that, and that will filter out the high frequency component and maintain the low frequency component. Then after inverse Fourier transform, here shows the signal back in the time domain. It is the similar waveform of my original signal. However, the signal has been smoothed out. The high frequency component has been filtered out. And we can use same method to look into the function of each element in both time domain and the frequency domain. The first element is the oscillator. Oscillator can be represented by this symbol. Here is the oscillator. The oscillator input is an arbitrary phase phi. The output is a pure sine wave using a cosine function, cosine 2 pi f0 t plus phi. If the initial phase phi is a constant, and then the oscillator output has a frequency of f0. The oscillator can be represented using this equation. The output signal yt equals to cosine 2 pi f0 t plus phi. Now, in general, phi can be a function of time. If phi t equals to, for example, cosine 2 pi f1 t, then the output of my oscillator is cosine 2 pi f0 plus f1 t. Then I have a sine wave with frequency f0 plus f1. Here shows the oscillator output in both time domain and the frequency domain. Because we choose cosine function as the output, so in the frequency domain, we will have two magnitudes, one in the positive frequency, in this case f0 equal to 10 Hz, and also at the negative 10 Hz, because we are using cosine as my output. Theoretically, if my waveform signal, if the oscillation can be represented by an exponential function e to the power j 2 pi f0 t, then in the frequency domain, I will have only one spike in positive sense, and that's in positive 10 Hertz, and I don't have this term. The reason I'm using a higher spike is because it has twice the energy of the original half, so it moved it. And then we will have, this is the, in frequency, we will see only one spike in the positive part. Now to implement that, what we can do is we are using an oscillator that will produce a cosine function multiplied by the signal st for upconversion, for instance. And then I can use a phase shift of pi over 2, 90 degree, and that gives me a sine function multiplied by this st. In that case, I will have both the real part and imaginary part of the signal. And here is my cosine 2 pi f0 t. And here I have a sine 2 pi f0 t. So it gives me both the real part and imaginary part of the upconverted signal. The second one is a linear filter. For a linear filter, the symbol is using a block diagram, and from signal processing we know here the ht is the impulse response. Capital HF is the system response. So linear filter can be represented mathematically using a convolution in the time domain. Yt equals to ht convolved with ut, where u is the input signal, h is my impulse response. It can be spread out in this integration form. In discrete time digital signal processing or discrete time signals, we can write the output yk, a convolution that equals to sum hi multiplied by u k subtract I, where I is from negative infinite to infinite taking integers. And that is the convolution in the discrete time domain. For the frequency domain part, a filter is simply a multiplication. Therefore, I will have this block diagram that gives me YF, Y is capital Y, frequency domain, equal to UF times HF. And similarly, in the discrete time representation, we can write out YK equals to, Y omega equals to U omega multiplied by H omega. Here is okay. If we are using a causal finite impulse response linear timing invariant system, that means I'm using this HI, but HI is only valid, only non-zero when I counting the time I from 0, 1, 2, 3. And then because it's finite, I have a finite span, so from 0 to 2. And therefore, in the expanded equation, that means that my current output, depending on the current input multiplied by this impulse response, one of the parameter, the previous input multiplied by H1, and two sample past, the signal multiplied by H2, and that gives me the current output. That's the causal system because it only depending on the current input and the past inputs, which makes sense. It does not depending on future input. That's causal. We have also have this finite impulse response because H has a finite span, 0, 1, 2, only span of 3 symbol periods. Okay. This element is implemented in the time domain when we design the filter with these parameters of H. In the frequency domain, it's easy to look at the effect. The frequency domain view is simply a multiplication. So for example, if my original signal is a white input, meaning that I have all frequency components, if we go through a low-pass filter, I will have the lower frequency. If we go through a bandpass filter, I will have a frequency component within two frequencies, F star and another F star. This is F low, F high. If going through a high pass filter, then the higher frequency that I have here, but the low frequency being suppressed to a near zero. There's a MATLAB code very easily that we can simulate a linear filter with low pass, band pass, and high pass features. We will see that when we are dealing with MATLAB simulations. A sampler can be implemented using the symbol. It's simply a switch. When the switch is on, I'm going to take an observation or going to measure the input. So the switch is on every time steps that is parted by t sub s, which is the sample period. Then I will going to take this discrete time signal and written in this form, k is the time index. Sampler is easy to look in the time domain, and in the frequency domain, we know from the digital signal processing, if in one domain is discretized and in the other domain it is periodic. So the effect in the frequency domain is that suppose I have the signal look like this. Signal look like this. If I sampled it, the signal look like this. If I sample that on these points, and that will give me some periodicities in the frequency domain. So instead of have just one around DC here, I'll have another copy here and another copy here. And this copy is centered at frequency Fs, which is the inverse of sampling period. On the other hand, if I have a periodic signal in time, we know in the other domain it will be a discrete discretized signal. So in the frequency domain, we will see a discretized signal in frequency domain. I only have valid numbers of here, f, 2f, 3f, 4f, 5f. Within these samples, they are undefined. A downsampler is to decimate the digital signal into a sequence with even a loose structure, loose samples. In this case, m is a downsampling rate is an integer greater than or equal to 1. So we will have here, and the original signal is x0, x1, x2, x3. If I'm downsample that with the downsampling rate m equal to 2, I'm going to decimate and only take x0, x2, x4, and take a subset of the original signal. From a frequency domain view, what we did is we are changing the sampling frequency. Therefore, there is an effect called aliasing may occur. From the sampling theory, we know that if the signal look into the frequency domain look like that, here is 0, here is the maximum frequency in my original signal. Let me call that Fm. Nyquist rate, or the sampling theory, tells us if I sample that with a sampling frequency Fs greater than or equal to twice the maximum frequency, then I do not have any aliasing effect. In fact, what I have here is, because I'm doing the sampling, I will have a copy here around Fs, I have another copy here around 2Fs, another copy as 3Fs, and a negative Fs, so on and so forth. Because Fs over 2, which is this point, Nyquist frequency that is greater than or equal to Fm, there is no aliasing effect in this case. If we do downsampling, we remove Fs down the direction towards 0, so this copy will move to the left. And in the case that if it's moved to somewhere here, for instance, then I will have this aliasing effect because these two tails, they overlap, and then give me some corruptions in my original signal. Downsampling is useful if my original sampling frequency is much larger than the highest frequency in the signal. Downsampling can be used in any other smart ways if you can avoid aliasing effect, or if you can do something to remove the aliasing effect. For example, there is a modern technique called sub-Nyquist sampling, which indeed they sample at a very low frequency, sub-Nyquist. But because of they are doing some smart things to avoid the aliasing, they avoid the copies of different copies they on top of each other, and in such a way can retrieve perfectly original information, and that is something being using in the modern communication receivers. Here is a signal UT going through the sampler and a downsampling with a downsampling rate of 2. We can see the original frequency domain signal in amplitude looks like this. It's a UF absolute value from negative 2 Hz to 2 Hz, for example. Once we do this sampling, I will have some other copies at the sampling frequency. In this case, 10 Hz is my sampling frequency. So I have another copy in the frequency domain here, and another copy here at 20. And then there's another at 30, at 40, negative 10, negative 20. Then the signal going through the downsampler with rate of 2, that means this sampling frequency will be divided by 2. So it becomes 5 Hz. Therefore, I will have all these copies of 5 Hz, 10 Hz, 15 Hz, so on and so forth. In this example, because my sampling rate is higher than twice or 4 times of the maximum rate of my original signal, therefore when I downsampled with 2, I still don't have any overlap, don't have any aliasing. That is a valid downsampling process. Static nonlinearities have many different forms. For example, squaring. Squaring is I have an input signal, and then I have its square, and that is my output of yt. So yt equals to u squared t. For example, considering a sinc function in time domain, and in the frequency domain, what we have is a rectangular function, because sinc function doing Fourier transform, that's a rectangular function. Vice versa, rectangular function, Fourier transform, sinc function. So if I have the sinc function, now if I work with sinc function square, so you will see that's something like this. So it's squared. Let me using another color. So that's sinc square, peak here, peak here, peak here, peak here. Okay. Then in the frequency domain, what do we have? Well, a rectangular function convolve with another rectangular function, because it's a sinc multiplied by a sinc. So it's a rectangular convolved with another rectangular function. A rectangular function convolved with a rectangular function, that will give us a triangle function. Mathematically, that gives us a triangle function. So what we have here is I have a triangle function like this. And obviously, the frequency components has changed. It's not only change in the amplitude, but also the span of the frequency will change. So that is a nonlinear operation that change the frequency parts. Quantization is another example of nonlinear operation. Quantization is you map the signal to the nearest quantized alphabet member, or the quantized levels. So in the frequency, we will see the frequency actually will be added some additional components. These are the harmonics added to the input spectrum. We have some additional spectrum, so the frequency part will change. The next element is the mixer. The mixer is a multiplier. So we have a signal ut multiplied by another signal. Now multiplexer, in this case, we are using that as a upconverter. So upconvert using a carrier frequency of f. So multiplied by cosine 2 pi ft plus an initial constant phase phi. That gives me the output yt. A multiplexer is a function multiplied by this cosine function. In the frequency domain, we will see that this is the original ut, uf, that we call that DC baseband signal. Then here is my cosine function. Of course, that's cosine function in the frequency domain, plus phi. And we look in the frequency domain using Fourier transform. So we have those two spikes. And these two combined together, then it will upconvert my original signal uf into this new yf, which has those two components here and here, centered at carrier frequency of 1000 Hertz, another one at negative 1000 Hertz. Now mixer or upconvert itself is a nonlinear operator. So indeed, we have changed the frequency. We'll add some additional frequency in the output. And a mixer is that I have those multipliers. Maybe I have another one multiplied by cosine 2 pi f1t plus another phase of theta, and multiplied by a u prime t. And this is the signal I can add on to the original signal sending out. They're not going to affect each other, because if f1 and f are apart, so here is f1, and then the u prime t, suppose it's the same two spike, so it will be here and here. And that is the frequency division multiplexing. I multiplex multiple samples, multiple signals and send them together. However, they don't affect each other in this case because they are upconverted using different carrier frequencies. The last element is the adapter. Adapter is to adapt to some changing situations, changing environment. We have a signal of U, and then the signal is being modified. We are taking the signal U, also some of the parameters of my modification of this adapter, and the adapter operation is using F, then give me an output of Y. Y is some of the signal that is need to be close to a desired output. We can have a feedback loop, in this case, to adjust all these adaptive parameters. So we have the quality assessment. For example, we may have some training symbols training out. We want to see if the training symbol Y, and if I know the desired signal of D, want to minimize D, T subtract Y, T, absolute value square in the minimum mean square error sense. So I want to minimize that. Using this, let me erase here, the signal here. Using this to tune my signal parameters or the adapter parameter theta. So recursively, I adjust the parameter theta of my adapter, and then using this loop, and then they can refine my system, make sure it will change the varying environment. For example, it can fight with the carrier offset. So you want to have a phase difference or a carrier difference approaching 0. If it's not 0, if it's positive, I'm tuning toward direction that is negative adjustment. If the carrier offset is negative, I'm adjusted toward a positive adjustment. Eventually, I want to make sure that the carrier offset is zeroed. And the same thing can be applied to the timing issues. Timing issues is a symbol. I want to make sure that I can have a matched filter, and a filter exactly matched to the symbol span. If it's not, I will go do some additional adjustment. There are some other use of adapters. For example, the adapters may adapt to the changing system environment. So if I'm going to track a signal, however the signal is changing, the frequency is changing, so I need to track to the signal. And then I can use an adapter to do that. Some other examples, for instance, I have an adaptive notch filter compacting newly materialized narrowband interferer. What it says is, if I find or observe some narrowband interference, what I want to do is I want to make my linear filter look like this. I have a notch filter, so it will notify a certain part of my frequency from FA to FB, for instance. And this part exactly maps this interference range. Therefore, I can remove the interference by tuning this notch filter. And there are many other examples, very interesting examples using adapter. So these are all the 6 elements of a communication system.